Okay, so we're back, and this is our final problem. We are in section 3.5 to 3.6, and this is it. We're going to be done with this. So we have a shear spring. It's made from 2 blocks of rubber, each having a height h, a width b, and a thickness a. The blocks are bonded to 3 plates as shown. If the plates are rigid and the shear modulus of the rubber is G, determine the displacement of plate A when the vertical load P is applied. Whew, use small strain analysis. Okay, so I'm going to push down here, and when I push down here, I'm going to want to find out what this delta is in terms of all of these variables. So the first thing I'm going to do is I'm going to draw a free body diagram of equilibrium. Okay, whenever you don't know where to start with free body diagrams. So if I start with a free body diagram, then as I'm pushing down here on P, on my plate, okay, we're going to be met with shear forces here on the right and left side of the plate. So if I sum forces in the y direction, I'm going to find that V equals P over 2. Okay. And if I look at one of these rubber blocks, then, so we're going to just kind of peel this rubber block off. And we're going to kind of try to draw this kind of a little bit. Okay, if I have V pushing down, then on the block, if P is pushing down, shear is going up on the plate, then shear has to be going down on my block. So I'm looking at this glued connection right here, the glued connection. So I have V pushing down, and I can see that we're going to end up with that deformation then because we have V pushing down. I also know that it's acting on this area. So I need to go back and address the area. If this is A, okay, and this is H, then this must be B. So that area has to equal B times H. You see that? B into the back, H is the height. So when I'm looking at this picture, it's kind of like the front section of that. Okay? Now if I look at my free body diagram of deformation, if I continue to look at this side of my plate, here's my plate. Here is the very left plate. Here is that rubber piece that we're looking at. Here is the middle plate. So we're pushing down in force P, and what's going to happen is it's going to end up going down. The rubber's going to go down right here, and that we can see is an angle change, so that is gamma. That is gamma. So what I'm going to do is I'm just going to go ahead and push this. I know it starts here, but my plate is now down compared to where I started. Okay, so I push down P, and we said the picture over here says to call this delta. That's what I'm pushing down. When I'm looking at geometry, I know that this is A. So I've pushed down with this force P. It is being split on each side because of symmetry, pushing back equal and opposite, which means we're pushing down on the rubber blocks, which makes sense. It's coming down. This is our shear strain gamma, and here is delta. It says to use small strains, so normally we would think of gamma as tangent delta over A, but remember with small strains, we don't have to do that. We don't have to say that tangent delta or tangent gamma equals delta over A. Small strain says we can just go straight to radians and delta over A. Okay, so I have my equilibrium. I know the force that's acting on that rubber pad, and I have my deformation, and I have it all defined. So we're looking at a lot of shear stress. So I want to remember that shear stress is a shear force over area. I can relate shear stress to shear strain with my shear modulus G, and I know that shear strain, when I'm looking at small strains, is going to be that delta over that length. So if I want to take this in variable form and calculate an equation for delta, I have to fill in everything else. I'm told it has a shear modulus G. We know that V and A are shear stress, and we know how it relates to shear strain. So let's just rewrite this equation. if I have shear stress equals G times shear strain, I could rewrite this as V over A equals G, and my shear strain is delta over A based on our variables that we have here. I know that using statics that V is actually P over 2. So let's do that, P over 2. I know that that area, okay, attachment, it's the area into the page, is B times H, that's my area, equals G times, okay, gamma is delta over A, looking at small strains, delta over A. That G kind of looks like an A, so let's just kind of go ahead and change that. And now we can rewrite this equation so that we have delta equals, we're going to have P times A, bring that 2 down, 2BH divided by G. So we have an equation now that relates the amount of deformation, the amount of pushing down, the amount of delta that took place with that axial, with that that perpendicular load P. It's P times A divided by 2BHG. So if you know the material and you know the force P and you need to limit this value, you now have variables that you can play with, okay? And maybe the H right here is flexible, or maybe this A is flexible. And so by playing with your variables, you can now optimize what it is that you're wanting in terms of deformation. So it's just, it's being able to draw free body diagrams of the force and the deformation and understanding how everything is related back through these 3 equations. And that's it.